y'all. Today we're going to look at 1.5 on graphing exponential growth and decay. In this section, we're going to be able to graph exponential growth and decay functions and be able to find specific values of exponential growth and decay. This standard is from FIF 0.7, and this is being able to graph functions from their symbolic representations, including indicating key features of intervals, intercepts, increasing, decreasing, and such. Remember that we are told in the standard to graph simple cases by hand and complicated cases with technology. And again, we're looking at simple cases a lot with these examples, but some of the problems that we're going to look at later on will be more complicated with the values that they have, and we'll want to use our calculator or Desmos for that. So let's go ahead and look at example 1. So in example 1, we're going to look at exponential growth. Exponential growth is modeled by the following equation. Y is equal to a times b to the x power, such that b is larger than 1. And so when we graph these, remember we talked about in the review section 0.2, where we talked about exponential functions, we talked about how just to graph like 2 to the x or 1/2 to the x. Well, now we're throwing in a new value in front of that and wanting to see what it does to affect it. And so in example 1, we're going to graph y equals 3 times 2 to the x. And so we want to set up a table for this. And so remember, we're going to use our x. We're going to have 3 times x squared. And then eventually we'll get our y values that we'll be able to plot on this coordinate plane. And so we're going to use -1, 0, 1, and 2 for our values. Now, when we graph exponentials, we need at least 3 points, but we could use 4, we could use 5. 3 to 4 is typically the ballpark you want to be in. So let's look at this first value here. 3 times 2 to the negative first. And so remember that a negative exponent does not change the sign of the number. It changes its orientation in a fraction. It finds its reciprocal. And so we're going to be multiplying 3 times 1/2. Well, 3 times 1/2, remember you can put this 3 over a 1. 3 times 1 is 3. 1 times 2 is 2. So we get 1/2. And so we're at the order pair, -1 and 1.5. Right there. Okay. So let's look at 0. 3 times 2 to the 0. Well, remember that anything to the 0 is 1. So 3 times 1 is just 3. So we get the order pair 0, 3. Okay. Let's look at 1. 3 times 2 to the first. Remember, anything to the first is itself, so this will be 3 times 2, which is 6. And so we get the order pair 1, 6. And finally for 2, 3 times 2 squared. And so 3 times 4, because 2 squared is 4. And 3 times 4 is 12. So we get the order pair 2, 12. And that's going to be a little bit off the top of our screen. Now, remember when we talked about exponentials at the start, we talked about how they have an asymptote. And the default asymptote for an exponential function is the x-axis. And so we're going to come in here and draw our asymptote along this x-axis here. And so remember that an asymptote is a line that a graph cannot cross. And so when we connect these points, we're going to see that this graph is going to come down like this. And it looks like it would eventually cross, but it's actually going to slow down and get closer to that x-axis, but never actually cross it. And so the line of the x-axis is y equals 0. And that's actually the answer to the asymptote here. Our asymptote is at y equals 0. And as long as we don't have any vertical translations going on, our asymptote is going to stay exactly right there. Now, domain and range, remember we've talked about domain and range before. Domain is the x variables, right? How far to the left, how far to the right does this graph go? And so as we look at this graph going further and further to the left, it's actually going to go to -infinity. It doesn't stop going to the left. When we look at it going to the right, we see this parabola gets not the parabola, but the exponential gets tall very quickly. But as it's going up, it's still going to the right. And if we go further and further and further, if we were to look at this on Desmos, we would see that this will continue going up, but it's also going to continue going right. And so this will go all the way out to positive infinity. And so we could also say that the domain is all real numbers, but this notation is called interval notation, and it is important to know both ways of expressing domain and range, both as an inequality and as an interval. Okay? And so our domain here is all real numbers, negative infinity to positive infinity. The range, remember our range is the y values. And so how low and how high does this go? Well, we look at how low it's going, right? It cannot cross this green line, this asymptote of y equals 0. And so remember we talked about how it's going to get closer and closer and closer, but is it ever actually going to become 0? No. If you go to Desmos and you go really far out there, it's eventually going to say 0. But Desmos is limited in its calculation to only so many decimal places. And so when it rounds the answer and it's going 0.000000001, it can only show like 3 or 4 decimal places, and so it just rounds that to 0, which is a kind of a limitation of what Desmos can show you in those small values very close to 0. And so the range here is going to start at 0, and we're going to use a parenthesis here because we cannot be 0. If I could be 0, I'd have a bracket, that square bracket, but I can't be 0, so it's a parenthesis. And then we look at how high it's going. Well, this graph's going up, and it goes up quickly, but it never stops going up, and so this is going to go to positive infinity. We could also write this as y is greater than 0. And so, again, we need to know either notation, the interval, or the inequality to be able to express this domain and range. Okay? And so there's our graph. We've identified the asymptote, the domain, and the range, and we've got these points plotted. Let's go ahead and look at example B. So in example 1b, we're going to look at y is equal to negative 2 times 3 to the x. We want to identify the asymptote, the domain, and the range like we did in the previous problem. And so we're going to set up our table again. And so we're going to start with our x. And we'll have our negative 2 times 3 to the x. Give ourselves a little space to do some work. And we'll have our y values so we can plot these ordered pairs. And so again, we're going to choose negative 1, 0, 1, and 2 to see what this graph is going to do. And so plugging in negative 1, we get negative 2 times 3 to the negative first. And remember that a negative exponent is not going to make it negative, it makes it a fraction. And so we get negative 2 times 1/3, and so it gives us negative 2/3. And so our first order pair, negative 1, negative 2/3, sit about right there. Then we go to 0. Negative 2 times 3 to the 0. Well, 3 to the 0 is 1, so negative 2 times 1 is negative 2. And so 0, negative 2. We go to 1. Negative 2 times 3 to the first. So negative 2, 3 to the first is 3. So negative 2 times 3 is negative 6. And so negative 1, negative 6. And finally 2. Negative 2 times 3 squared. 3 squared is 9. So negative 2 times 9 is negative 18. And so we'll get our last order pair. And 2, negative 18 is way down here. And so we see that this graph looks like this. And again, it's going to get really close to that x-axis the further we go out. But that asymptote here is stopping it from crossing the x-axis again. And so when we look at our asymptote, domain, and range, our asymptote is still that x-axis at y equals 0. Our domain is going to be all real numbers again. It goes from negative infinity to positive infinity. And our range this time, look at what it does. What's the lowest that these y values will get? Well, it goes down forever, so it's going to go all the way down to negative infinity. What does it come up to? Well, that graph gets stopped at the x-axis, and again, it's coming up, but it's going to stop before we can get to it. And so we're going to stop at 0 with a parenthesis. Again, it's not a bracket, it's a parenthesis here to show that it gets close, but will never be 0. And so that is how we graph these problems. In example 2, we're going to look at how to deal with the actual word problems and how we find the information that we need to plug in for this formula. So let's look at those. So another way of expressing our exponential growth model, our y equals a times b to the x, is to use this model, y equals a, parentheses, 1 plus r to the t. And so when we look at this formula, it's very similar, but it does show us the growth happening because the a will be the initial amount. Where did we start? The r is what percentage we're growing at. Now, of course, we got to convert percents to decimals to be able to work with them. And t will be our time period. And so we're going to be plugging in values into those three places. And so let's look at example 2 and how we're going to use that formula. And so the number of rabbits on a farm was 48 in 2021. The rabbits' population was 45% every year, accounting for births and deaths. How many rabbits will be on this farm in 2030? And so we're going to use our formula, y is equal to a times 1 plus r to the t. And so we're going to plug in everything that we know into this formula. And so first off, we know that there are 48 rabbits in 2021. And so this 48 is my initial value. The 2021 is just telling me when that occurs. And that's going to be important information for the second part of this problem. And so we're going to go y is equal to the 48. 1 plus, that's just part of the formula. We have to have it when we do this formula. And we see that the population growth is 45%. And so we're going to convert that percent to a decimal. And remember, we're going to move that decimal 2 places. In this case, moving it forward 1, 2, and we get 0.45. And so 0.45 will go here. And then we can put the t on the back side. And that would be the equation of it. We can combine together the 1 and the 0.45 and get y is equal to 48 times 1.45 to the t. And that would simplify it down a little bit. But now we need to actually answer the question that's being asked. How many rabbits are going to be on this farm in 2030? Well, we need to know how far it is from 2021 to 2030. Now, one method of doing this is calling the first year, year 0, and then just resetting the whole scale. And so how many years is it from 2021 to 2030? Well, that's 9 years. And so 2030 becomes 9. And that's actually what we're going to plug in for t is 9. And so we get our 48 times 1.45 to the 9th power. And when we go to our calculators, we can plug this all in one fell swoop, and we will get the final answer. And so we plug that into our calculator, and I don't know if you can see that or not, but we get the answer 1,360.0449. Now, we're talking about rabbits here. Can we have a partial rabbit? No. And so we've got to round this appropriately. And so our answer here is going to be 1,360 because we can't have 0.04 of a rabbit. I'm sorry, that would be a rabbit's foot. You're out of luck. And so this word problem needs a word answer, and so our word answer here would look like this. The farm would have, or will have, 1,360 rabbits in 2030. And so again, relate the problem back to the problem. Don't just leave your answer as y is equal to 1360. Actually state what it means and all the context of this problem. All right? And so now we're going to look at exponential decay in the next two examples and see how it's similar but different from what we looked at before. So the key difference between exponential growth and exponential decay is what the b value can be in this formula. So we're using the same formula, y is equal to a times b to the x, but now our b has to be between 0 and 1. And so we see that with example 3 and what we're going to graph. And so we're going to graph y is equal to 3 times 1/2 to the x. And again, identifying the asymptote, the domain, and the range. And so let's look at this graph and set up our table. And so set up our table, we have x. We're going to have 3 times 1/2 to the x. Give ourselves some space to do some work. and our y. And we're going to go from -1 to +2 like we've done on all of these examples. And so plugging this in, we're going to get 3 times 1/2 to the -1st. And so remember that a negative power is going to take that fraction and take its reciprocal. And so we're going to get that's equal to 3 times 2 to the 1st, or just 3 times 2, and that's going to give us 6. And so our first order pair is -1, 6. And then we can go to 0. So 3 times 1/2 to the 0. Remember, anything to the 0 except for 0 is 1. And so we get 3 times 1, which is 3. And so 0, 3. We go to 1. 3 times 1/2 to the 1st. Anything to the 1st is itself. So 3 times 1/2. Remember, we can make that a fraction. And so 3/2, or 1.5. And so we're here. And finally, one more, going to 3 times 2, or not 2, but 3 times 1/2 squared. And so 1/2 squared is 1/4. And so 3 times 1/4 is 3/4, or 0.75. And so we'd be sitting about here. And so we take those 4 points, we're going to draw our line. And our line is coming down like this. And again, our asymptote is on the x-axis. And so we will curve closer and closer to it, but never actually become the x-axis because our asymptote is sitting there. And so to answer that question, the asymptote is y equals 0. Again, for everything we're graphing in this section, the asymptote is on the x-axis, and it's at y equals 0. The domain, still all real numbers. It's going from -infinity to +infinity. So we can put that in. And then the range, what's the lowest that this graph can be? Well, again, it's approaching that asymptote, getting closer and closer to 0. So we're going to go from 0, and it's going up forever, so it's going to go to +infinity. And so we see our graph there. All right. So again, we graph these up with the ability to be able to find these points and know their domain and range. Okay? It doesn't matter what values we have, or what's the a or what's the b, as long as they're within the specific values. Now, the big thing to know is about exponential growth and exponential decay. In exponential decay, we see that this function starts high as we're on the left side and comes down and gets closer to that x-axis as we go further to the right. So it is a decreasing function, hence why it's called a decay function. In exponential growth, we started out very flat, almost on that x-axis, and eventually we shoot up very quickly. And again, we're growing, because we always talk about graphs as we go from left to right at the end of the day. Okay? I'm going to skip example B in the notes here and move on to example 4. If you're interested in example B, ask me about it and I'll be happy to go over it with you. But looking at example 4, remember that we talked about in example 2, another way to look at exponential growth was y equals a times 1 plus r to the t. Well, if we're decaying like we are in this case, that plus becomes a minus. Everything else is still the same. The a is still the initial amount. The r is what rate it's now decaying at, what percentage we have. And the t is still our time. And so looking at example 4, we get y is equal to a times 1 minus r to the t. And we're going to see where everything is going to go in this example. Now, are we always going to know if it's going to be a plus or minus beforehand? No. We actually need to read the problem to know, is this growing or is this decaying as we go longer and longer in time? And so let's look at this question. And so we've got a town has a population of 125,000 in 2020. And so that's our initial value. And then we say that the town is decreasing, so there's our decay, at a rate of 2% per year. And so remember that percent is going to get converted to a decimal. And so 2 places, 1, 2, so 0.02. And we want to know in the end, what is the population of the town in 2030? And so we know what our t is going to be when we go to find this. And so writing the equation, we're going to plug everything in. Y is equal to 125,000, 1 minus our r of 0.02 to the t. And simplifying that, the easiest way to always think about these is to think, what's a dollar minus however many cents I'm subtracting? So what's a dollar minus 2 cents? Well, it's 98 cents to the t. And so that would be our equation of it. And so if you're ever asked what is the equation modeling this situation, you would leave the t in place. But we actually want to find what's happening in 2030. So we're going to call 2020 year 0. And then 2030, well, how far is that from 2020? Well, that's 10 years. And so plugging in the 10, y is equal to 125,000, 0.98 to the 10th power. And so we're going to go to our calculator and see what we get. And so going to our calculator, we see that we get 102,134.1009. Now, again, we're dealing with people here, so can I have half of a person? Well, even Lieutenant Dan with no legs is still a whole person. He would be counted as a whole person on the census. And so we'd have 102,134. And so in 2030, the town would have a population of 102,134. And so again, with these examples, make sure that you relate the problem back to its original context. Again, have the context in place. All right, so if you got any questions, let me know. But that is the end of this lesson. I hope you all have a good one, and I'll catch y'all next time.